We're really cooking with gas. Okay, so let's see here. We were looking at these problems, chapter 15 practice problems. So let's take a look here. It says protons HA and HB are homotopic and antiotopic, diastereotopic. Well, mesotopic is not even a thing. We can scratch that off of there. Was anybody able to answer this one? One of the things you could do is the replacement test. You could do this, where we take, and we put this, oops, we got an extra carbon in there. Okay, then we put our chiral center like this. Okay, and so what I'm going to do is I'm going to copy and paste this. So I'll just copy this and paste it over here like this. And we know that one of the protons is going to be going down like this, and we'll call this one HA, doesn't matter. And one of them is going to be going up like this, HB. And we can see that those are diastereomers of each other. Now, the way the replacement test is done in the book is they do it with deuterium. So that you have a deuterium here, and then you'd have a proton going down, and then here you'd have a proton going up. But you can clearly see that these are diastereomers of each other. And so these two protons are diastereotopic. All right. The next one, it says protons HA and HB in the following compound, homotopic and antiotopic, diastereotopic, or mesotopic. Well, again, there's no such thing as mesotopic, so we can scratch that off of there. We can also scratch off diastereotopic because there's no chiral center in the molecule. Now, homotopic versus enantiotopic. Well, with enantiotopic, we look for an axis of symmetry. And in enantiotopic, we look for a plane of symmetry. You can clearly see that there's an axis of symmetry here in the molecule, right? If we rotate this 180 degrees, you wouldn't be able to differentiate between those two protons. Therefore, they are homotopic. So again, we have an axis of symmetry, symmetry, like that. Question number 3 is, how many signals would you expect to see in this proton NMR spectrum? So we've got CH3, O, and then we've got CH2, and then we've got CH3. Did anybody answer this question? How many unique signals would you see here in the NMR spectrum? Yeah, thanks, Ariana. You'd see 3, right? Each single one of these, the 2 methyl groups are both unique. They both have different chemical shifts, as does the methylene. And so the answer would be 3 signals is what we would see. The methyl on the far left here, that's not split by any proton, so this would give you a singlet. It's not asking for this, but I'm just going to pencil it in. Down here, these 3 protons would give you a triplet because they're coupled to 2 protons. And the methylene would give you a quartet because it's coupled next to the 3 protons in blue. How many signals would you see in the, excuse me, the NMR of the following compound? So I'm going to write it out like this. So if we put CH2, you can see you've got 4 methylenes here. I'm just going to do it like this. And CH2. And you can see why I'm color coding this. It's because we have an axis of symmetry running through the molecule like this. So you can see the 2 hydroxyls are chemically equivalent. The 2 methylenes in red are chemically equivalent, and the 2 methylenes in blue are chemically equivalent. And so we would get a total of 3 signals for this compound. In question 5, how many signals would you see in the proton NMR of this compound? This is called meta-ethyl benzoic acid. Did anybody get an answer for this one, for 5? Somebody has 7? Yeah, I think that's reasonable because there's no symmetry, right? No symmetry in this compound. And so every proton is going to be unique. This is a unique proton. This proton is unique. This proton is unique. This proton is unique. This one is unique. This methylene is unique. And this methyl is unique. So that gives you a total of 1, 2, 3, 4, 5, 6, 7. So we have a total of 7 signals for this compound. If you were to try this one and identify how many signals would you see in the carbon-13? So in the carbon-13 NMR, even though it's not asking for it, every single carbon in here would be unique. So you'd have 6 in the aromatic ring, 7, 8, 9. So you'd have a total of 9 signals in the carbon-13. So a lot of signals. Anyhow, I'll just scribble that out here. We'll just put 9 signals. Okay, number 6. Which of the indicated protons would appear the most downfield in the NMR spectrum? So remember, downfield is highest chemical shift. Chemical shift. Okay, most deshielded. Most deshielded. So if I look at all of these, could anybody tell me which one of these is going to be most deshielded or have most electron density removed from around it? Yes, it's going to be these ones, isn't it? Number 4 or D, right? And the reason why is because you have a dipole between the carbon and the oxygen, right? Pulling electron density away like this. We know that oxygen is the second most electronegative element in the entire periodic table. And so if you were to estimate what the chemical shift is for that methylene, for those CH2 protons, you start with the baseline of 1.2 parts per million, right? And then you would add 2.5 because it's alpha to the oxygen of an alcohol. So you'd end up with 3.7, right? Something like 3.7 ppm, approximately. That would be the chemical shift of those. All right, same thing in, or sorry, not the same thing. This one, we actually have to determine all of the chemical shifts and then choose which one is the best answer. So let's start with number 1. So for number 1, we have the baseline of 1.2 parts per million. And then it's alpha to the oxygen of an alcohol. So we're going to add 2.5 parts per million. And so that gives us 3.7 parts per million. So that's going to cross off C and D. So it's a battle between A and B. All right. Let's look at these protons here. So number 2, I'll kind of scribble those maybe over here. So we start with the baseline, which is 1.2 for a methylene. Oh, I guess I should use the same color. 1.2 parts per million, which is the baseline for a methylene. Then these ones are alpha to a carbonyl, right? This is the alpha to this carbonyl. So we add 1 part per million for that. And then they are beta to the hydroxyl. So we're going to add 1/5 of 2.5, which is 0.5 parts per million. And you tally all that up, and you get a total of 1.2 plus 0.5 plus 1. So that gives you 2.7 parts per million. And so we can see that the answer is hopefully A. And it should be because there's no difference between these protons here. But anyhow, let's just do it. So we have 0.9 for the baseline. And then we add 1 for the carbonyl. We get 1.9 parts per million. And so the answer must be A is the correct answer. All right, number 9. It says a compound with the molecular formula C8H14 has the following NMR spectrum. Which of the following is the correct number of protons giving rise to each signal? So here they gave us, we have a total of 14 protons. So it's we'll say 14 protons. And so what we're going to do is we're actually going to get our ruler out. And we're going to measure each one of these step curves. Now, bear with me here. So we've got a total of, let's see, I need a new prescription, but anyhow, I'll do my best to read this. So it's about 10.5 millimeters, this one. Jeepers. 10.5 millimeters. Then I'll measure the one on the end next. That's around, so let's see here, 15, 16, 17, 18. Looks to me like it's around 18. And if you got a better measurement than me, then my hat is off to you. Like I said, Mr. Dion needs a new prescription pretty bad. Let's see here for this one. So this is 1, 2, 3, 4, 5. So 50, looks to me like it's about 55. Just put 55 millimeters. I realized that I carried an extra sig fig with one of them. Let's see here. Probably not, Savannah, as the answer. Probably not. So we're going to divide each one of these by 10.5, divide by 10.5, divide by 10.5. So here we get 1. If you take 18 and you divide by 10.5, you get 1.7. It gives you around 1.7. And then here, if you take 10.5, you get around 5.2. So it's close to 5.2. So if it was 1, so it's kind of close to, if you double them, right? If you double them, it's not very good. Like these aren't the best step curves in the world, but if you double each one of these, you get 2. This one comes close to 3. Now this one gives you over 10. So, but either way, if you have 2 and 3, and they have to be different, so that would add up to 5. And so that would mean that this one is about 9. Maybe my measurement is off a little bit, but I've done this problem before and I didn't write down the answers. So it's 2, 3, and 9. So it would be A would be the answer. You might want to double check my measuring if you print this out, but you won't be asked to measure any step curves on the quiz, okay? No step, you don't have to hold a ruler up to the screen or anything like that. Let's try a couple more. Which of the following compounds gives a proton NMR spectrum containing only a singlet? So if we start with A, so it's 1,1-dichloropropane. So if we write this out, that's this compound, so 1,1-dichloropropane. Well, that's not true because this is going to give you a triplet. This is going to give you 3 plus 1, so it gives you a quintet. And this one here is going to give you a triplet as well. So A is not the answer. Let's try B. B is 1,3-dichloropropane. So that's this and this. Well, that's not going to be it either because this is split by a total of 1, 2, 3, 4. So this is going to give you a quintet, right? And each one of these is split by 2 protons, so they'll give you a triplet. So this is the same triplet here. It just integrates for a total of 4 versus 2 protons. In C, it's 1,2-dichloropropane, definitely not. So you have 1,2-dichloro. Well, this is wrong for tons of reasons. This is a doublet. This one is going to be 1, 2, 3, 4, 5. So this one's going to give you a sextet. And then this one here would give you a doublet. So that's just plain wrong. And then in D, this better be the right answer. It's 2,2-dichloropropane. Well, hell yeah. You're going to, both of these are chemically equivalent, and they're just going to give you a singlet because they're not split by any protons. And so the answer is D. All right. And the last one does the same kind of thing. It's which one of these are going to give you 2 singlets. So now we have to figure out the multiplicity for everything. So we have an aldehyde proton here, aldehyde proton here, aldehyde proton here, and an aldehyde proton here. We'll just scribble all those in. So for this aldehyde proton, you get a singlet. This is a singlet, and this is a singlet. So you get 3 singlets for A. So that can't be the answer. So let me just scribble this in here. That's 3 singlets. For the second one, you get these 2, which are chemically equivalent, and then you get these 2. So that would give you 2 singlets. Those aren't split by anything. So the answer has to be B. If we look at the number 3, definitely not. This will give you a singlet. This will give you a singlet. This is going to give you a quartet. And this is going to give you a triplet. So that's not right. And the next one, this one gives you a singlet. This one gives you a singlet. And this gives you a singlet. So that's 3 singlets. And the last one, you get a singlet for this. You get a singlet for this. You get a singlet for these. And you get a singlet. So that's 4 singlets for that one. So the answer is number 2. Is the one that gives you 2 singlets. So what I want you to do before class tomorrow morning is I want you to try questions 11 through 22. So I'd like you to try all of these problems, and we're going to take a look at them tomorrow morning. Also, depending on the time that we have, I would like you to take a look at the remainder of these problems, but we might not look at these because these all come from Klein. So you have the solutions to all these. The reason I post them is because there's no way for me to get you to write this down in your notes or something. So I just post them on slide. So maybe tomorrow morning we'll take a look at those other problems and this one as well. So we'll do this one 15.63, so Tuesday. All right, there we go. Wow, I'm down to my three most